virtual classroom for our subject ME Laboratory 1, in which we are going to learn the use of the instruments and devices that we found in engineering laboratories. For this activity, we're going to demonstrate and learn how to use the instruments for determining the properties of fluids and solids, like density, specific gravity, and viscosity. So let's start. Our activity is measuring the three interrelated physical properties of fluid. And for the learning objectives, after this activity, you are going to learn how to determine the density of various liquids by measuring the relative density or the specific gravity using a universal hydrometer, and how to measure the density of a small solid using a pycnometer, and how to measure the viscosity of various liquids at atmospheric temperature and pressure using a falling sphere viscometer. Before we proceed with our activity, let us first discuss some of the terminologies. So density is the mass of an object divided by its volume. We commonly use the unit of kilograms per cubic meter, or in English is slug per cubic feet. Specific weight is the weight of the substance divided by its volume. So it is in weight over volume, or in pounds over cubic feet, or in metric is Newton over cubic meter. Specific gravity is the ratio of the density of substance to the density of water at 4 degrees Celsius. Our reference is the water at 4 degrees Celsius in determining the specific gravity of the fluids. We use water at 4 degrees because it is said that water at this point, or at this condition, has attained its maximum density. So the specific gravity is unitless. Viscosity is the resistance to flow. It defines the thickness or how sticky is the fluids or the substance. The unit for viscosity is in Pascal second or in kilogram per meter second. Buoyancy is an upward force exerted by a fluid that opposes the weight of a partially or fully immersed object. Drag, in fluid dynamics, drag is a force acting opposite the relative motion of any object moving in respect to a surrounding fluid. Inertia is the resistance of any physical object to any change in its velocity. And terminal velocity is the maximum speed reached by the falling ball through a viscometer. The determination of the properties of fluids is attributed to the works of Archimedes and Stokes. So our activity is governed by this principle and law. For Archimedes' principle, it states that any body completely or partially submerged in a fluid at rest is acted upon by an upward or buoyant force, the magnitude of which is equal to the weight of the fluid displaced by the body. While the Stokes law states that the drag force on a sphere of radius moving through a fluid of viscosity at speed is given by the following equation. F for drag force equals to 6 pi times the radius of a ball times the viscosity times the speed of the moving ball through a fluid. With this activity, we have two assumptions. So the first assumption is that the flow around the ball is laminar and the Reynolds number is less than 1. In this case, viscous force dominates the inertia force, or the inertia plays a very small role in this condition. The next assumption is that the terminal velocity is sufficiently slow and the body does not experience acceleration and the net force is 0. So let's say if we drop a ball into a hydrometer filled with fluid, while the ball is moving into the fluid, at a certain point, we assume that the ball attains the maximum velocity, which is a terminal velocity that is sufficiently slow and the body does not experience acceleration, and that the net force is 0. So we are assuming, though the ball is falling through the fluid due to gravitational acceleration, but we also assume that the acceleration is 0. Once the acceleration is 0, the net force is 0. And that assumption, we have come up with an equation which is the weight minus the buoyance force minus the drag force equals to 0. So if we see a particle falling through a fluid at your right side with a velocity v, the gravitational acceleration is acting on g, and the sigma here is the density of the solid. So the weight is acting downward, while the buoyant force in Archimedes' principle is said to be acting upward, and also the drag force. So if we look at the free body diagram, we see that the weight is positive and the buoyant force and the drag force are negative. So with our equation here, if we will substitute a value that is the density of the solid times the gravitational force times the volume, which is 4/3 pi and the radius r cubed for the volume of the sphere or the ball, minus the buoyant force, which is the density of the fluid times the gravitational force times 4/3 pi r cubed. Minus 6 pi times viscosity times speed times the radius equals to 0. So if we rearrange the equation and we want to determine the viscosity, we will get this equation for viscosity equals to 2/9 times r squared times the gravitational force times the change in density, which is the density of solid minus the density of liquid, over the speed, which is the speed of the fall. So this equation, we will determine the viscosity and we will use this as we get all the data that we need. For this activity, we are going to use the following instruments: a hydrometer, which will use to determine the specific gravity. So it floats upright and provides the specific gravity. So for this activity, we're going to use the universal hydrometer. Next is the pycnometer. It is a standard container often provided with a thermometer for measuring and comparing the densities or specific gravities of liquid or solids. So in our activity, we're using a 50 ml of pycnometer, and we have a separate thermometer. Next is the falling ball viscometer. So it measures the viscosity of Newtonian liquid by measuring the time required for a ball to fall under gravity through a sample filled tube.
This is the apparatus that we will use for this activity. So we will show each of the items or each of the instruments that we are going to use. So this is the universal hydrometer, which we use to measure the specific gravity of the substances. And this is the hydrometer jars. We have two, one for the glycerin and one for the castor oil as our sample. At first, we'll fill it with water. Then we'll insert this hydrometer, universal hydrometer, into the jars. And also, to measure the density of the small solids, we have here the pycnometer. So this is a 50 ml pycnometer. And then, to measure the viscosity, so this is the viscometer jars, which will put the balls inside. So this is already filled with glycerin and castor oil. So these are the metal balls which we will drop inside the viscometer jars. Also, we need a thermometer to measure the temperature for each of the fluids, the glycerin and the castor oil. And also, we have the stopwatch for the time and the weighing scale to measure the weight. Now we're good to go. We can start our activity.
For our first procedure, we are going to determine the density of liquid using a hydrometer. And we're going to complete this table with our sample fluids, the water, glycerin, and castor oil. We are going to take the temperature reading for each of the fluid and the specific gravity using a hydrometer. After we obtain the data, we will use this equation below to solve for the density of the fluids, which is the density of the fluids equals to the density of water at 4 degrees Celsius times the specific gravity that we have obtained. The density of water at 4 degrees Celsius is 1,000 kilograms per cubic meter. So let's start.
Before we start our activity, let's make sure that our apparatus is level using this level gauge. Make sure that the bubble is on the center, or else let's adjust the table stand. So for now, our hydrometer jar is already filled with water, which will be our first sample. And then we will insert the hydrometer, universal hydrometer, into the jar. Let it settle and stabilize before we will take the reading at the surface of the fluid. So if our water is at 4 degrees Celsius, our reading must be 1 for the specific gravity. But since our water is not 4 degrees Celsius, there's a slight difference, but it's almost 1. So if we'll take the temperature, so the temperature here says it's 25 degrees Celsius. So the specific gravity is almost 1. Very slight difference. Now we remove the water and we will replace it with glycerin. So we'll pour the glycerin up to the top in a level in which the universal hydrometer can float. Same thing we did with the castor oil for the second hydrometer jar. Then we'll insert the universal hydrometer into the jar with glycerin. And we have another universal hydrometer. We can use it in the castor oil. So let it settle and stabilize. And as you notice, there is a difference of the level between these two fluids. This is due to its different thickness and density. Now we'll take the measurement at the surface level of these fluids. But as you notice, there's a small bubble formation at the surface of the fluids. So let it settle. But if there's still a bubble formation, what we'll do is to take the reading just below the bubble lines or the bubble formations. Same thing with the castor oil. Just right below the bubble formation. So this procedure is to measure the specific gravity of the fluids, which we'll use to find the density of these fluids in our table. So we'll take the temperature of each of the fluid, then we can record the data which we'll use in our table.
As soon as we have the data, we'll write down in our table provided. So for the water, we have the temperature reading of 25 degrees Celsius. For glycerin is 26 degrees Celsius, and for castor oil is 27 degrees Celsius. For specific gravity, water is 1, glycerin is 1.2, and castor oil is 0.9. So with this data, you can determine the density using the equation below. For the next procedure, we are going to determine the density of solids. So we will use this table for our data. So let's start.
We are on the second stage of our data collection. So for this procedure, we are going to determine the density of the small solids using this pycnometer. So this is a 50 ml pycnometer. First, we'll have to measure the mass using this weighing scale. Measure the mass of the empty pycnometer. So we'll make sure that before using the weighing scale, it is well calibrated. Then after we measure the mass of the empty pycnometer, we fill it with water and we closed using the lid. Then we will remove the excess water and make sure that there's no bubbles that form inside the pycnometer. Then after this, we take also the mass for this pycnometer with water. Then record the data. And after that, these metal balls it will use. So we'll take some of the metal balls and measure the mass, and using these empty cups. First we will weigh the empty cups, which will put the metal balls in it. So we'll just subtract to take the mass of the metal balls. Subtract the weight of the mass of this cup. Then we have it. Record the data. And then back to the pycnometer, which is already filled with water. We will remove the lid and pour the metal balls inside. So you have seen little excess or displaced water. Then we will measure the mass and record the data, which we'll use in our.
After we gather the data, we can substitute these data to determine the mass of liquid, the density of liquid, and the density of solid. Our end result will be the density of solid, which we will use in our next procedure. So with these tables provided, this is in a tabular form for writing all your data, and provide the value for the mass of liquid, the density of liquid, and the density of solid using the equations that we have provided. We are now on the last and the final stage of our data collection. In this procedure, we are going to determine the viscosity of fluids. With the table provided, we will use the sample fluid, the glycerin, and the castor oil. And the ball diameter is 1.5 mm and 3 mm. We're going to record the temperature for each of the fluid, the fall length, and the time of fall. In this activity, you're going to conduct at least 3 trials to drop the ball inside the viscometer. After that, we'll record the average sphere fall velocity in meters per second. And with the equation provided, to solve for the viscosity, we're going to determine the average dynamic viscosity in Pascal second.
We are now on the last and the final stage of our data collection. So in this procedure, using the falling sphere viscometer, we are going to determine the viscosity of the substance using these metal balls, which we are going to record the time of fall, and the length of fall. So here for the castor oil, we will drop the metal ball, and also for the glycerin. So just the same procedure for each of the fluid. And you can see that when you drop the ball, there's some graduation, and make sure that the the fluid is filled up to the top, because we will take the reference point at the top to start with our timer. And at the bottom, there's a line for the 0 point. Now we start the timer when it reached the reference point. So you can see the metal ball is moving downward up to the bottom, but we stop the timer at the last line before it reached the bottom. So we'll repeat the procedure for each of the viscometer jars for glycerin and for the castor oil. So we have just dropped another ball, and you can see it moving downward. And the same procedure, from the reference point we start the timer and we stop the timer at the 0 line. There we have it. And this procedure we'll just repeat for the others, different sizes or different diameters of metal balls for each of the substance, for the fluids, for the castor oil, and for the glycerin. Then we'll record the data, which we will use in our table to determine the viscosity of the substance.
After conducting at least 3 trials for each of the fluid, the glycerin and the castor oil, using the ball diameters of 1.5 mm and 3 mm, we have recorded the temperature 26 degrees Celsius for glycerin and 27 degrees Celsius for castor oil. The fall length is the same for each of the fluid, with the viscometer jar is 200 mm, and the time of fall for glycerin using the 1.5 mm ball is 7 seconds. Using the 3 mm ball diameter is 3.6 seconds. For castor oil, dropping the ball of 1.5 mm is 5 seconds, and for 3 mm is 2.5 seconds. With these data, we can determine the average sphere fall velocity in meters per second. And with the equation provided in determining the viscosity, we can compute the average dynamic viscosity in Pascal second using the previous information that we have obtained, like the density of solid and the density of liquid. Now we can complete the table by solving this equation. For the final output of our activity is the part 2, the results and discussion, in which you're going to present the filled out tables for the 3 procedures. Table 1, the density of liquids, Table 2, density of solids, and Table 3, viscosity of fluids, with the tables that we have provided. And also, you're going to compare the results obtained for density and viscosity against the standard table for the liquids tested, and comments on the accuracy of the results. That's all for our activity. I hope that you have learned how to use the devices and the instruments in determining the properties of fluids and solids. Thank you.